Hello and welcome. This is the third video in chapter 22. This is going to be a little bit more quantitative. The first couple of videos were really qualitative, that first one being about the series of experiments, and then the second video being about how objects can become electrically charged and their sort of atomic makeup, conductors versus insulators, and how to charge conductors versus how to charge insulators. So in this one, we see the fundamental force law governing two electrically charged point-like objects, and that's Coulomb's law. You will notice that, well, there's three versions of it for each different combinations of electric charge, but it's strikingly similar to gravity, actually. This is a law that you will have seen in chapter 13 on Newton's theory of gravity, where we had the gravitational force between two celestial bodies being proportional to the product of the masses and the separation of their distance squared. That's where that r squared comes. And so we have to have a constant, capital K, like we do for capital G. And the capital K, that just makes the units correct, because we have newtons on the left-hand side and then Coulomb squared divided by meters squared, and so the units for K have to cancel out. So this is the first one where we have two negatively charged objects. Similarly, if we have two positively charged objects, and then finally, if we have a single particle that's positively charged with a single particle that's negatively charged, we obviously see the attractive force. And so a couple of remarks about this law is that it is only for particles that can be modeled as points, or particles that can be modeled as spheres, in particular on the outside of particles that can be modeled as spheres. Because one thing we're going to be doing in this course is we're going to be extending Coulomb's law to different shapes of electric charge, right? Objects don't have to, in the case of gravity, most objects that we apply gravitational forces to are, besides rocks and people and things near the surface of the earth, most shapes for which Newton's law of gravitation applies are spherical. But in the case of electrostatics, you can have any shape electric charged object exerting force on any other shape. So we're going to extend that idea. So what we do with Coulomb's law is with this form we can only really consider a couple of examples where you have two or more electrically charged, say, point particles, and they form, for instance, the sides of a polygon, like a square, or triangle, or rectangle, or something like that. What you'll notice about capital K, though, is that it is has units, and the constant is 9.0 times 10 to the 9. And this is a little summary that you'll find in the textbook for when to use Coulomb's law and how to apply it. One remark that we make from the very beginning about capital K is we actually ignore it. We don't do this in gravity, but we do it in electrostatics. So what we're going to do is we're going to take the capital K and we're actually going to redefine it in terms of a 1 over 4 pi and what's called a 1 over epsilon naught. Now that seems kind of strange to do at the very beginning. Why are we making Coulomb's law look more confusing? Well, it's going to turn out that there's a lot of fundamental laws and relationships that we'll find in chapters down the road where the 4 pi actually goes away and we're left with something just called epsilon naught. So epsilon naught is called the permittivity constant. Some textbooks and some resources you'll find online will call it the permittivity of free space. And that's kind of interesting because it turns out that every object, every solid or liquid or gas or everything will be described by a certain permittivity. And this is just the baseline permittivity, 8.85 times 10 to the negative 12. And notice that the units are different. The units are inverted from the units of K. So there's a couple things I can think of off the top of my head where epsilon naught will be more fundamental than cap k. But cap k really is the force constant between two charged objects. Okay, so what kind of problems, kind of homework exercises are you going to be expected to do with these types of problems? Simple things like this, where you have three charges, two or more charges, and you have to find the electric force felt by one of them due to, say, the other. And so we can go through this one in a reasonable amount of detail. It's not that hard. I'll show you some tricks along the way. So we have three electric charges. The one in the middle, charge B, that's the one where we want to find the net electric force on. And so A is at the top here. That's magnitude 1.0 nanocoulombs, right? The lowercase n indicates 10 to the negative 9. And it's got a distance in centimeters. And so same thing for C. And so what does a free body diagram look like before we move on? Well, let's work on it. Since A and C are both positively charged and B is negatively charged, they're both going to feel an attractive force. So we'll see something like this. That'll be the force of A on B. And we'll also have something down. That'll be the force of C on B. Whoops, that's supposed to be a B. Okay. And how do I calculate this? Well, I'll use the space on the left-hand side to try and calculate that. It's not that big of a deal. I'll write it out, though. And I'm using my hand, so bear with me. So F of A on B. Okay. We directly use the formula for Coulomb's law that we just wrote down. So the force constant is 9 times 10 to the 9, and I'm going to use the units way at the end. That's the cap K. A is 1.0 times 10 to the negative 9, and then B, 2.0 times 10 to the negative 9. Now, you divide all that by the distance squared. Well, the distance is 2 centimeters, so it's going to be 2 centimeters squared, or 0.00040, I guess, square meters, right? If the distance between the charges is 0.02 meters, then when I square that, squaring the decimal place, I go down a few more places. So that is the formula. That's what you would type into your calculator that you would enter in. Notice, since we're doing nanocoulombs, this is great because the nano in one of the charges, say, for instance, first one, it'll cancel with the 10 to the 9 in the permittivity constant. And so really, what I would do, if I was plugging this into a calculator and typing it in, I would just say, well, 9 times 2 at the numerator is 18. So I have 18, 10 to the negative 9, divided by 0.0004, and we get 4.5 times 10 to the negative 5 newtons. So that's the magnitude of the upward force that charge B feels due to charge A. And we can do the same thing with the second charge combination, B and C. Same 9 times 10 to the 9 for the constant. Oh, I should have written units out in front. But now we've got 2 times 10 to the negative 9, 2 times 10 to the negative 9, and the denominator, since it's only 1 centimeter, when you square that and convert to meters, it's 0.0001 square meters. And so that all has units of newtons. And so when you work that out, you actually get 3.6 times 10 to the negative 4 newtons. And to be honest, we have a lot of scientific notation here, but it's kind of easy to just do this straight up because really the answer, looking at all these numbers, we got 9 times 2 times 2, right? That's like 9 times 4, which is 36, right? So we have 36, 10 to the negative 9 at the top, 1, 10 to the negative 4 at the bottom, right? So 36, you know, and then you just go through the scientific notation. So 3.6 10 to the negative 5, or sorry, 3.6 10 to the negative 4, that's the force at the bottom. And so it's a factor of 10 bigger. So basically, when you sum these forces, when you go to sum these forces, you have the upward one, that's 4.5 10 to the negative 5. The downward one, that's like 36 times 10 to the negative 5. So, and those are both newtons, and so they cancel, and so the result is that charge B feels a downward force of 36 minus 4.5, right? That's like 36 minus 4, you know, tack on an additional 0.5. So that will be 3.15 times 10 to the negative 4 newtons. That's the net force. And the direction is obviously down. Right? Since this is one-dimensional, you don't have to worry about components. But since we're dealing with forces, we will, if we do charge arrangements that are not collinear, then you will have to contend with components. All right. So that's an example of using Coulomb's law. Coulomb's law, in my opinion, is pretty easy to do because you're given the formula and you just have to plug in the numbers. The only thing where folks might get into trouble would be when we're dealing with different vector components, and so you have to use the vector components. Okay, so that is it for this specific video. What we'll find in the fourth and final video for this chapter is that there's going to be a far more important besides that of force between electric charges, and that will be of field. So stay tuned for that one. As usual, thanks for your time. We'll see you at the next video. Take care.